All right. So we are discussing about linear functions. Okay. So there are different ways to represent a linear function. We have seen that in the previous class. So one way is to see in the previous class we have seen different ways of representing a linear function. See, by the way, we are discussing heart of algebra, which forms 33% of the questions, which forms 33% of the syllabus of your SAT math curriculum. Okay, and in that heart of algebra area, we have already seen linear equations, linear inequalities in one variable. Now we have come to linear functions. Okay, linear functions and then graphical representation form they ask a lot of questions from this area. I mean, these are very easy questions. Okay, so you can easily score score well in these questions, but the basic idea should be very clear. Okay, what are linear functions, and how our real world situation, how our real world scenario can be modeled as a linear equation. It's a very common thing. Okay, a lot of questions will come from this area. So please listen carefully. If you have any doubts, please get back to me immediately or over WhatsApp. Okay, so in the previous class, we have seen different ways of representing a linear function. Okay, one way is just using a mapping diagram where you have numbers which are mapped to another set of numbers. That is one way to do it. Okay, another way is you can represent them as a set of ordered pairs. Say, for example, if your linear function is this way, I'll make some small changes. Say, let's say this is 5, this is 7, this is 9, this is 11. Suppose your function is this way. One way is to represent using a mapping diagram. Another way is using set, and the set will contain all the ordered pairs. Okay. Another way is to represent it on a graph. So you take a graph. Okay. You just mark these ordered pairs. So you have, for 1, you have 5. So you mark 1, 5. For 2, you have 7. So you mark 2, 7. You have 3, 9. Mark 3, 9. 4, 11. You mark 4, 11. Okay. So that is another way to represent a linear functions. So the graph of a linear function will always look like a straight line. Okay, you have to remember that. Another way is using an expression. Okay, an expression that will give the relationship between the x values here and the y values here. Okay, that is another way. Say, for example, in this case, your f of x will be of the form, or you can say this is y. Your y will be of the form. See, 1 is mapped to 5, 2 is mapped to 7, 3 is mapped to 9, 4 is mapped to 11. So there will be a relationship that represents the connection between x and y. There will be an expression in terms of x and y that will show the relationship between x and y. And for linear function, how to derive that expression, how to arrive at that expression, that we will see soon. Okay. For the time being, I'm going to write that expression. I'm going to do a mental calculation and write that expression. You have to verify that whether it matches. Okay. I'm just going to write it directly. Okay. So this is going to be 2x plus 3. Y will be 2x plus 3. Can you check these numbers and tell me if I'm right? Can you just check these numbers? When x is equal to 1, is your y value 5? And when x is equal to 2, is your y value 7? When x is equal to 3, is your y value 9? When x is equal to 4, is your y value 11? Can you check and let me know whether it matches? Yes. Does it match? Does it match? Tell me, everyone, please tell me whether it matches all the numbers, all the 4 ordered pairs. Yes, it does, right? Now, how did I arrive at this number? How did I arrive at this expression? These are typical questions, okay? I'll teach you how to arrive at this expression. Soon we'll come to that, okay? So this is another way to represent a function, okay? So another way to represent a function is you can write y is 2x plus 3, or you may write f of x is equal to 2x plus 3, okay? Or you can write 2x minus y plus 3 is equal to 0, okay? Or what you can do is you can have a table, an input-output table, where you have x and y values represented as a table. So you have 1, 5, and there is 2, 7, 3, 9, and 4, 11. So these are the different ways to represent a linear function. Okay. Now, given a function, how do you figure out that it is a linear function? Okay, that also we have seen. How from the graph, it will be a straight line. If you have an expression, it will be a linear equation in both x and y. You look at the power of x and y, the highest power will be 1. Highest power of x and y will be 1. Okay. And from the table, how will you figure that? From the table, how will you know? Here, if for the constant differences in x, here the difference is 1, here the difference is 1, the differences in y will be also a constant. 2, 2. See this? So these are the different ways to figure out that a given function, a given relationship between x and y is a linear function. Is that clear? Tell me, is that clear? Yes? Got it? See, if the function is not linear, say for example, if the function is not linear, for example, if you have, say, for 1 we have 1, for 2 we have 4, for 3 we have, say, 9, 4 we have 16. Now, if I take constant differences in x values, the differences in y values are not the same always. See, we have 3, here 5, it's 7 here. You understand the difference? So this is linear. This is not linear. Is that clear? Clear for everyone? Yes, please give me a yes. See, this is what we saw in the previous class, and we had a problem sheet based on these ideas. Okay, so let's quickly see that. And before seeing that, I'm going to give you some of the real world scenarios where you will see linear functions. Okay, so please listen carefully. Some of the real world scenarios where you will see linear functions. Okay, the most common scenario is cases where there is a direct variation. Okay, or you say there is a direct proportion. You can say direct proportion or direct variation. See, think of this example. Think of this example. So you are working on a job, and for every hour of work, you're getting $20. So you're being paid $20 per hour. Okay. So for 1 hour, you get $20. For 2 hours, you get $40. Okay. For 3 hours, you get what? $60. This is what we call a direct variation or direct proportion. Remember studying this in very small classes, right? This is what we call a direct variation or direct proportion. This, in fact, represents a linear relationship. How? How can you say that this is a linear relationship? Okay. One way is by looking at the numbers. Say if you call this as x values and if you call this as y values, see that for constant differences here, the differences here is also constant. Here it is 20, it is 20 here, 20 here. Okay. So does that represent a linear function? Does this represent a linear function? Tell me, does this represent a linear function? The number of hours you work and the how much money you make. This is a relationship between these two. Is that a linear function? Tell me, please. Is that a linear function? Anyone? Hello. Are you guys with me? Are you with me? Yes, it is a linear function, right? Because one way to look at it is for constant differences in x, the differences in y are also constant numbers. Okay. Now you can come up with an equation that represents the number of hours. Say if you spend h number of hours and if you make m amount of money, there will be a relationship between h and m. Can you tell me what will that relationship? If you spend h hours working and if you make m money, there will be a relationship between h and m. What is that relationship? Can somebody tell me what will that relationship be? What will that relationship be? Between h and m, what will that relationship be? The number of hours you spend and the amount of money you make. Given that you are being paid 20 hours, $20 an hour. Please tell me the relationship between h and m, the number of hours you spend and the money you make. Hello. For 1 hour, it's $20. For 2 hours, it's $40. For 3 hours, it's $60. For h hours, how much money will you make? Hello. Hello, hello, hello. If you're confused, do let me know. If you know the answer, please let me know. Please give me a response. If you're confused, let me know. Please let others. Okay, simple question. For 1 hour, you're making $20. For 2 hours, you're making $40. For 3 hours, you're making $60. So what is the math? For 1 hour, it is 1 times 20, right? For 2 hours, it's 2 times 20. For 3 hours, it's 3 times 20, right? For 4 hours, it's 4 times 20, right? Is that clear? Because for every hour, you're getting $20. 2 hours, it's going to be 2 times 20. Yeah. So for H hours, what will be the amount? For H number of hours, what will be the money that you'll be getting for H hours? H times 20, right? H times 20. Say, for example, H is equal to 10. How much money will you make? H is equal to 10. How much money will you make? 10 times 20, $200. Is that clear? Is that clear? Others. Yes. So for H hours, you're going to make 20 times H, or H times 20. H times 20 is the money that you'll make. So you can write this as 20 times H. Now, this is a linear relationship between your H and M. Okay, this is a linear relationship between H and M. Why? Because why do we call this as linear? Look at the power of H, it's 1. Look at the power of M, it's 1. Now, what does 20 represent here? What does 20 represent here? What does 20 represent here? It represents the constant rate at which you are paid, right? Every hour you're getting the same amount of money. So this represents the constant amount, constant rate at which you are paid. Okay. And this is what we call as the constant of proportionality. Constant of proportionality. Or sometimes you must have learned it as constant of variation. Constant of variation. There's a direct relationship between the number of hours you will work and how much money you will earn, right? Is that clear? Another example, I'll give you another example. Say you're driving a car, okay? You are driving at a constant speed of 30 miles per hour. You're driving at a constant speed of 30 miles per hour, right? How much distance will your car cover in 1 hour? How much distance will you cover in 1 hour? How much distance? You are driving at a constant speed of 30 miles per hour. How much distance will you cover in 1 hour? See, in what does this represent? This represents your speed, right? What does this tell me? What does speed tell me? Speed tells you how much distance you will cover in 1 hour. It says 30 miles per hour. So in 1 hour, you're going to cover 30 miles. So in 2 hours, how much will you cover? 60, yes. Okay, in 3 hours, you will be covering 90 miles. Okay, so if I'm telling you in T number of hours, how much distance will you cover? In T number of hours, how much distance will you cover? Yeah, that's all. T times 30, right? So this is going to be T times 30 or 30T. T times 30 or 30 times T. Both are same. 3 times T or 30 times. So this is your distance covered. So your distance covered is equal to 30 times T. So if you put T is equal to 1 hour, your distance is 30 miles. If you put T is equal to 2 hours, you get 60. For 3 hours, you get 90. In 10 hours, you can cover how much? 300 miles. Got it? So this is what we call a direct relationship or a direct variation or a direct proportion. Okay, because things change at a constant rate. Things change at a constant rate. And this is the constant rate at which you are covering the distance. Right? And that is what we call the speed. In this case, this is what we call as a speed. In the previous case, it was your rate at which you are being paid. That was $20 per hour. Okay. And this is your speed. Okay. So you would have already seen this relationship, right? Distance is equal to speed times time. Distance is equal to speed times time taken. Speed or velocity. Okay. Velocity is a different concept actually, but for the time being, you can call it velocity, no problem. Okay. Is that clear? This example is clear, right? Yeah. So this is a linear relationship. Why? Because you look at the power of t, it's 1. You look at the power of d, it's 1. Okay. So this is a very simple case of linear function. Your y value will be some number, some constant times x. Your y value will be some constant times x. Okay, your y value will be some constant times x. For example, your distance covered was 30 times time. Your money earned was 20 times number of hours. Okay, so in general, a direct relationship or what we call a direct proportionality, okay, or direct variation will be in the form y is equal to k times x. Is that clear? Y is equal to k times x. Is that clear? Y is equal to k times x. Is that clear? Okay. And this k is what we call the constant rate of proportionality. The constant rate of proportionality. So this is a very simple example from your smaller classes. Okay. In smaller classes, you learn this as a direct relationship between your distance and time, direct relationship between your number of hours and your wage. Okay, but now we can represent this as a linear function. This is a linear function. Why? Because the relationship between your x and y, okay, is a linear relationship. Clear? Okay, your linear relationship will always be of the form y is equal to mx plus c. In this case, like in this case, the idea is very simple. This constant is 0. That's all. The constant number is 0 here. Okay. Now, my question is, if I draw the graph of this thing, if I draw the graph of m is equal to 20h, m is equal to 20h. So you have h here on the x-axis and m on the y-axis. There is something very peculiar about the graph of m is equal to 20h. Can you tell me what will be the peculiarity of the graph of m is equal to 20 times h? Can you tell me, please? If you know the answer, please tell me the answer. Otherwise, you just say, I don't know. Please give me an answer. That's all. If I draw the graph of m is equal to 20 times h, there will be something peculiar about the graph of this function. What is that? What is that property of the graph? If you know the answer, please tell me. Otherwise, just say you don't know. Please give me a response anyway. Anybody? Anybody? See, first of all, since this is a linear relationship, since m is equal to 20h is a relationship. Sorry, this is not y. This is your m. Okay. Since this is a linear relationship, it will be a straight line. Okay, the graph will be a straight line. But there is something very remarkable about the graph. Okay, it's simple. The graph will pass through the origin. Graph will pass through origin. Why? Because when your h is equal to 0, so when you plot m is equal to 20 times h, when your h is equal to 0, your m value is 0. Okay, so h is equal to 0, m is equal to 0 is nothing but your origin. So your graph will pass through the origin. Okay, so always remember, if you have a function of the form y is equal to some k times x, graph of this function will always pass through the origin. Please remember, please note it down. When you have a function of the form y is equal to k times x, the graph will pass through the origin. All right? Yeah. The second common example for linear function is what we call and arithmetic sequence. Arithmetic sequence or progression. Arithmetic progression. Arithmetic sequence or arithmetic progressions. Have you seen arithmetic progressions in your 8th grade? Have you seen arithmetic sequence in your 8th grade? Do you remember arithmetic sequence in your 8th grade? Yes. Others? Have you seen this in your school? Arithmetic sequence? Say, I have a sequence of numbers. Say, for example, I have 1. Then I have 2, 3, 4, 5, 6. This is an example for a arithmetic sequence. In an arithmetic sequence, the difference between consecutive terms is always the same. Okay, here the difference is 1, difference is 1, difference is 1, the difference is 1, difference is 1. Another example is we have 2, 4, 6, 8, 10, 12, and so on. Here the difference is 2, the difference is 2, the difference is 2, the difference is 2, difference is 2. This is an arithmetic sequence. Another example is, say we have 1, and then there is 4, then there is 7, then there's 10, then 13, 16, so on. So difference is 3 here, difference is 3, here difference is 3, difference is 3, the difference is 3. This is an arithmetic sequence. Now tell me, is this an arithmetic sequence? 2, 4, 8, 16, 32, 64. Is this an arithmetic sequence? Is this an arithmetic sequence? Please give me a yes or no. 2, 4, 8, 16, 32, 64. Is that an arithmetic sequence? Is this an arithmetic sequence? No. Why? Why? The difference between consecutive terms is not the same. Here it is 2, here it is 4, here it is 8, here it is 16, here it is 32. The difference between consecutive terms is not a constant. So it is not an arithmetic sequence. Another example, I'll give you 1, 1, 2, 3, 5, 8, 11, 19. Not 11, 13, 21, 34, 55, 89. Is this an arithmetic sequence? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. Is this an arithmetic sequence? No. Look at it very carefully. Look at it very carefully. Is that an arithmetic sequence? Please look at it very carefully. Please look at it very carefully. No, it's not, right? Because, the difference is 0. This is 1. Here the difference is 1. The difference is 2. The difference is 3. Difference is 5. Difference is 8. Difference is 13, and so on. By the way, this is not a random sequence of numbers. This is a very popular sequence of numbers called Fibonacci or Fibonacci sequence. Have you heard of this name Fibonacci? Have you heard of this sequence before? Yeah. Okay. The first numbers are 1 and 1. Then you keep adding two consecutive terms to get the next term. So 1 plus 1 is 2, 2 plus 1 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. Okay. This is not an arithmetic sequence. This is not an arithmetic sequence. Okay. An arithmetic sequence will have what? The difference between consecutive terms as the same constant everywhere. Okay. Now, typically, let's see something. So if I have 1, 4, 7, 10, 13, 16, 19, so on. If I take this AP, if I take this arithmetic sequence, the difference between the consecutive terms is always a constant, and that constant is what we call as the common difference. So this is 3, 3, 3, 3, 3. This is what we call as the common difference. And it is usually represented as D. So in this case, D is equal to 3. In this case, D is equal to 3. This is what we call as a common difference of the arithmetic sequence. Common difference of the arithmetic sequence. Okay. These numbers are called the terms. A1 is 1, A2 is 4, A3 is 7. These are called the terms of the arithmetic sequence. So the first term is 1, the second term is 4, third term is 7, fourth term is 10, fifth term is 13, 16th term, sixth term is 16, 7th term is 19, and so on. Okay, so the fourth term is 10, fifth term is 13, sixth term is 16, and so on. Now we have 3, differences 3, differences 3, differences 3, differences 3. Okay. Now, can you tell me what will be the 10th term of this arithmetic sequence? A10. Can you tell me what will be the 10th term of this arithmetic sequence? A10. A1 is 1, A2 is 4, A3 is 7, A4 is 10, A5 is 13, A6 is 16. What will be the 10th term? Others, see, of course, A7 will come out as 19, A8 will come out as 22, A9 will be, you keep adding 3, right? So we have 25, A10 will come out as 28, right? See, since I asked you about A10, it's easy for you to figure it out. But what if I had asked A100? What if I had asked about 100th term? That will be a tough job. So here we are going to find out an expression for any term. Not only just 100th term, you can find out any term any term from this pattern. So there is a pattern. From this pattern, we are going to find out the expression for any term. Okay, so how can you do that? So let's say we need to find out a general term, nth term, nth term. Okay, so you see that the first term is a1. To get the second term, you are just adding d to it. Sorry, a2 is obtained as adding d to a1, right? And your a3 is obtained as adding 2 times d, right? Because from starting with 1, a 3 has been added here, another 3 has been added here. So 2 times d has been added to get a3. So to get a4, we have to add 3 times d. To get a5, we have to add 4 times d. Similarly, if you want to get an, we have to add n minus 1 to n minus 1 times d to the first term. Okay, n minus 1 times d. See, I'll explain once again. Please listen carefully. We have d is equal to 3. Your a1 is 1, a2 is 4, a3 is 7, a4 is 10, a5 is 13. In this specific example, to arrive at a2, we added 1 plus 3. To get a3, we added 2 times 3 to 1. To get a4, we added 3 times 3 to 1. a1 was 1. Okay. To get a5, we added 4 times 3 to 1. Is that clear? Is this pattern clear? Starting with a1, to get a2, you add 3. To get a3, you have to add 2 times 3. To get a4, you have to add 3 times 3. To get a5, you have to add 4 times 3. Is that pattern obvious? Is that pattern clear? Is this pattern clear? Yes. Yeah. Now to get the nth term, to 1, you add n minus 1 times 3. N minus 1 times 3. Why? Because to get a1, you added 0 times 3. Here you added 1 times 3. For a3, you added 2 times 3. For a4, you added 3 times 3. For a5, you added 4 times 3. So for n, you are going to add n minus 1 times 3 to 1. Add n minus 1 times 3 to the number 1. Is that okay? Is that okay? Yeah. So with this idea, you can simply find a10 as 1 plus 10 minus 1 times 3, which is 1 plus 9 times 3, which is 1 plus 27, which is 28. See, it's much easier now. Got it? Now, what do you see here? We have an expression for an, that is 1 plus n minus 1 times 3. So this is 1 plus 3n minus 3. So this is 3n minus 2. Your an is 3n minus 2. Now, if you consider this as an input-output relationship, you give n as the input, you get an as the output. An is 3n minus 2. Now, don't you think this is a linear relationship? This is linear. This is linear, right? This is a linear relationship. Don't you think it's a linear relationship? Don't you think that's a linear relationship? Because you have an is a linear expression in n. An has a linear expression in n. Is that right? It's a linear relationship in n. Is that right? Or you can instead of thinking as input output, you can think it as a table. You just consider it as a table. You have n and an. First term was 1. Your second term was 4. Your third term was 7. Your fourth term was 10. Your fifth term was 13, and so on. Now, if you take constant differences here, 1, 1, 1, 1, you have constant differences here, 3, 3, 3, 3. So does this represent a linear relationship? Does this represent a linear relationship? Tell me. Yes, it does, right? Why? Because if you take constant differences in n, the differences in an will also be a constant. If you take constant differences in n, the differences in an is also a constant. And that constant happens to be, the constant here happens to be the common difference, or that is what we call as the common difference. Is that clear? Is that okay? Is this clear? Please let me know. Yes. Yes. So you can generalize an arithmetic progression as, say, for example, in our case, if your first term is A, common difference is D. Suppose first term is A, common difference D. Your second term is obtained as A1 plus D. Your third term is obtained as A2 plus D, which will become, or you can directly write it as A1 plus 2 times D. Your A4 will be A1 plus 3 times D. Your A5 will be A1 plus 4 times D. Following this pattern, can you tell me what will A and B? What is AN? Please tell me what is AN? What is AN? Following this pattern, can you tell me what is AN here? Yeah, AN will be, in terms of A1 and D, what will be that relationship? See, A2 is A1 plus D, A3 is A1 plus 2D, A4 is A1 plus 3D, A5 is A1 plus 4D. Similarly, AN will be A1 plus yeah, very good. A1 plus n minus 1 times D. A1 plus n minus 1 times D. A1 plus n minus 1 times D. Is that clear? Okay. So what we just saw is, if I have a relationship between, if I think of this as an input-output relationship. Okay. this relationship is linear. This relationship is linear. The relationship between n and an is a linear relationship. So arithmetic sequence is another example, another common example for what we call as linear functions. Okay. So first example was the you have a constant rate at which things change. Okay. For example, there is a speed given. Okay. Another example was your salary per hour, wage per hour was given. Okay. So second type of linear function that we will encounter very commonly is arithmetic sequence. Okay. Now another example for linear function is unit conversions. Unit conversions. Another example is unit conversions. For example, if I am telling you that 1 inch is equal to 2.54 centimeters. 1 inch is equal to 2.54 centimeters. You know that 2 inches will be 2 times 2.54 centimeters, right? 2 inches will be 2.54 centimeters. 3 inches will be 3 times 2.54 centimeters. Similarly, if I have some I inches, what will be that number in centimeter? It will be I times 22.54, right? I times 2.54. I times 2.54. Clear? I times 2.54. Yes, is that clear? Is that clear? Please let me know. Yeah. So the same quantity when represented in centimeters, if it is C, and when represented in inches is I, the relationship between C and I will be C is equal to I times 2.54. C is equal to I times 2.54. This is going to be a linear relationship. This is going to be a linear relationship. Okay. This is going to be a linear relationship between C and I. Okay. So let us see one question. Let's see one question. The perimeter of a stadium is 1080 feet. Of the following, which is closest to the perimeter of the field, perimeter of the stadium, in meters? Okay. In bracket, it is given that 1 foot is equal to 0.3048 meters. The options are 330, 3540, 90, 108, 00. The perimeter of a stadium is 1080 feet. Of the following, which is closest to the perimeter of the stadium in meters? And it's given that 1 foot is equal to 0.3048 meters. Can you do the math and let me know the answer? It's not a difficult one. Please try it. The perimeter of a stadium is 1080 feet. Of the following, which is closest to the perimeter of stadium in meters, and the conversion factor is given. Conversion factor is given as 0.3048 meters. Yes, Olivia, the answer is right. Can you also give me an expression relationship between the same perimeter measured in the relationship between F and M? Say the same distance is measured in feet, same distance measured in feet and meters. What will be the relationship between F and M? The same distance when measured in feet and meters. What will be the relationship between F and M? Can you tell me that as well? Okay, very good. Okay, very good, very good. So now it makes sense, right? This is actually a linear relationship. The conversion between meters and feet, conversion between centimeter and feet, conversion between joules and calories. These are all linear relationships. Okay. The relationship between distance and time, the relationship between your money and the number of hours you work. Okay, these are all linear relationships. So there will be a lot of questions that can be framed from linear linear functions, which can be framed as a real world situation. Okay, word problems. Okay, please listen carefully. Here, 1 foot is 0.3048 meters. Okay, so 2 feet is 2 times 0.3048 meters. Okay, so thinking in the same lines, if I have 1080 feet, this is going to be 1080 times 0.3048 meters. Okay. And you don't have to actually pick up the calculator for this. Okay. You don't have to actually pick up the calculator for this because, when you look at the options, all the options are look at the numbers. These numbers are way apart. Okay. These are not close together. These numbers are not at all close together. Okay, these numbers are way apart. So you just need to get an approximate answer to get arrive at the answer. So if you have a calculator, you can actually plug in the numbers and get the answer. But what I'm going to do is I'm going to approximate this as 1000. This is approximately 1000. This is approximately 0.3. So your number is approximately what? 1000 times 0.3 is approximately 300. Your answer is approximately 300. And the answer closest to 300 is this one. Got it? If you plug in the number of values in the calculator, you will get the exact answer. But we don't need an exact answer because when you look at the options, there is 330, then there is 3000 something, then there is 10,000 something, then there is 90. These numbers are way apart. Okay. There are no numbers which are close. So there is no confusion here. Okay, you just need an approximate answer. Is that clear? Clear? The answer is close to 300. Others? Others, is that okay? Yeah, cool. So the relationship between, if I have, instead of 1080, if I have f feet, okay, that will be f times point, f feet will be f times 0.3048 meters. Okay, so the same distance measured in meters will be f times 0.3048. Okay, that is the relationship between m and f. Got it? Okay, anyway, I'll share a problem sheet with you with these ideas. Of course, we have a sheet which needs to be discussed. Please make sure that you spend some time. Okay, please make sure that you spend some time. Say half an hour or 1 hour per week is good enough. But make sure that you spend some time. Make sure that you spend some time. All right. Okay, then see you in the next class.